In lesson 14.3, you will verify trigonometric identities. And here are a few: the reciprocal identities, which we've looked at already, the tangent and cotangent identities, and the Pythagorean identities. First, let's write a proof for the tangent identity. And to do that, we're going to refer to the unit circle on the coordinate plane. And remember, the unit circle has a radius of 1. So if I drop a perpendicular from that point xy on the circle, drop a perpendicular to the x-axis, I form this right triangle with acute angle theta. And the horizontal leg has a length of x units, and the vertical leg of this right triangle has a length of y units. So in my proof, I want to use the definition of sine and find the sine of theta, which is opposite over hypotenuse, y over 1, or just y. The sine of theta is equal to y. And the cosine of theta, which is adjacent over hypotenuse, x over 1, simplifies to just x. So the cosine of theta is equal to x. Now the tangent of theta is equal to opposite over adjacent, or y over x. And now if I replace y with the sine of theta, and I replace x with the cosine of theta, I have the tangent identity. The tangent of theta is equal to the sine of theta over the cosine of theta. We can write a proof also for the Pythagorean identity. Again, referring to that right triangle in that unit circle on the coordinate plane, we can apply the Pythagorean theorem to it, stating that the sum of the legs squared is equal to the hypotenuse squared. And then just using the commutative property on the left here and writing y squared plus x squared equals 1 squared, which is 1. I can replace y again with the sine of theta, so that I have sine squared theta, plus replacing x with the cosine of theta plus the cosine squared theta is equal to 1, and this is just our Pythagorean identity. Okay, here we have two more, the cofunction identities and the negative angle identities. The cofunction identities just come from the fact that the acute angles of a right triangle are complementary, or they sum to 90 degrees, or pi over 2 radians. The negative angle identities refer to this right triangle in the fourth quadrant, where theta is measured in the negative direction. The horizontal leg is positive and the vertical leg is negative. The hypotenuse is always positive. So, applying the definition of sine, opposite over hypotenuse, negative over positive, we find out that the ratio for sine is negative in the fourth quadrant. Cosine is adjacent over hypotenuse, positive over positive, so the cosine ratio is going to be positive. And the tangent is opposite over adjacent, negative over positive, or a negative ratio. Okay, in our first example, we're given that the cosine of theta is equal to negative 5/13 and theta is between pi and 3/2 pi. We want to find the values of the other 5 trigonometric functions of theta. So again, on the coordinate plane, we're talking about theta between pi and 3/2 pi. So the terminal side of theta is going to be in the third quadrant, and this is the theta that we're finding the trigonometric functions of. And using the definition of cosine, adjacent over hypotenuse, we can label this leg and the hypotenuse of this right triangle, and we need to find the missing leg, so we'll use the Pythagorean theorem that hypotenuse squared, which is 169, is equal to the sum of the legs squared, and negative 5 squared is 25. So x is going to equal the square root of 169 take away 25, or that's the square root of 144, which is 12. So that leg is 12 units long and it's in the negative direction, so I'll label it negative 12. Okay, we already have the cosine, So let's find the sine of theta. The sine of theta is opposite over hypotenuse, so negative 12 over 13. And its reciprocal is the cosecant. So the cosecant of theta is hypotenuse over opposite, or 13 over negative 12. We already have the cosine, so we'll find its reciprocal, which is the secant. The secant of theta then is hypotenuse over adjacent, or 13 over negative 5. We need the tangent, and the tangent is opposite over adjacent, negative 12 over negative 5, which simplifies to positive 12/5. And the cotangent of theta is equal to adjacent over opposite, or negative 5 over negative 12, which is positive 5/12. Okay, in the second example on this page, we want to simplify an expression. When we simplify an expression, we want to simplify it to one function. And we use algebraic and trigonometric properties and identities to help us do that. Now I look at these two terms and I see that there's a factor of cosine in both terms. So I'm going to begin by factoring out that factor of cosine. So it leaves 1 minus the sine squared theta inside parentheses. Okay, and now because I have the sine squared theta, I think of the Pythagorean identities. I can replace 1 in parentheses there with the Pythagorean identity, sine squared theta plus cosine squared theta. And now inside parentheses I have a positive sine squared theta and a negative sine squared theta. They're going to sum to 0. So I'm just left with cosine theta times cosine squared theta, which is 3 factors of theta. So I'll write it as cosine cubed theta. And we've simplified it to one function. Okay, in the next example, we're going to simplify an expression and create one function. So I look at that numerator. In that numerator, we have a half angle. So I'll replace that sine of a half angle with a cosine of theta. And in the denominator, I have a secant of a negative theta. Now I don't have a negative angle identity for the secant, so I'm going to use a reciprocal. The reciprocal of the secant is a cosine, so I can write that denominator as 1 over the cosine of that negative angle. Okay, and then I can replace the negative angle in the denominator with just cosine theta. And now we don't divide by a fraction, we multiply by its reciprocal instead. So inverting that denominator and multiplying it to the numerator, I'm going to end up with 1 plus the cosine squared theta. And we've simplified it to one function. Okay, in problem 2, we want to verify or prove that this equation is an identity. And to do that, we can only change one side of the equation and show that it does simplify to the other side. So I'm going to choose to change the left-hand side here. Again, I have the secant of a negative angle, so I'm going to use the reciprocal identity. The reciprocal of the secant is the cosine. So I'm going to write it as 1 over the cosine of negative theta. And now, using the negative angle identity, I can replace 1 over the cosine of a negative theta with 1 over cosine of theta. And then using the reciprocal identity so that we don't leave the left-hand side as a fraction, the reciprocal of the cosine is the secant of theta. And now the left-hand side does equal the right-hand side. I can bring the right-hand side down and finish my proof. I'll use this little symbol to say therefore the left-hand side does equal the right-hand side. Okay, another proof. We're going to verify that this equation is an identity. Again, I'm going to choose to change the left-hand side and make it look like the right-hand side. And in the numerator, the reciprocal of the secant is the cosine. So I'm going to write cosine x times 1 over cosine x. And in the denominator, this is a Pythagorean identity, I can replace 1 plus the tangent squared theta, or x. You can use theta or x, and you'll see that they bounce back and forth using one or the other as their variable for this angle. I can replace 1 plus tangent squared x with secant squared x. And now in the numerator I'm multiplying reciprocals, so I just get a product of 1. And in the denominator, the reciprocal of the secant is the cosine, so I can write that as 1 over cosine squared x. And we don't divide by a fraction, we multiply by its reciprocal instead. So if I invert and multiply, I have the cosine squared x times 1, which is just the cosine squared x. So now I can bring down the right-hand side and say, therefore, the left-hand side of this equation does equal the right-hand side. Okay, in our last problem, we're going to verify that this equation is an identity. And again, I'm going to choose to change the left-hand side and make it look like the right-hand side. I have a sum in the denominator, and it's not sine squared, so I don't think to use the Pythagorean identity, but I do want to use the conjugate of that sum in the denominator. And I'm going to multiply this fraction on the left-hand side by a form of 1. 1 minus the sine x over itself. And then distributing in the numerator, I have secant x times 1. That's secant x. I have secant x times negative sine. That's negative sine x. Secant x. And in the denominator, when I distribute, I have the sum and difference of the same two terms, so I'm going to get a binomial. The first term is 1 times 1, and the second term is sine x times negative sine x, so negative sine squared x. Okay, and now in the numerator, I'm going to replace that secant x. Its reciprocal is a cosine, so I'm going to replace it with 1 over cosine x. And in the denominator, because I have sine squared x, I think to use the Pythagorean identity, and I'm going to replace 1 with sine squared x plus cosine squared x. Okay, and now in the top I have secant x minus that product, sine x over cosine x. And in the denominator, positive sine squared x and negative sine squared x sum to 0, so I'm just left with cosine squared x. Okay, and in the top, secant x minus, this is just the tangent identity, so I can replace sine x over cosine x with tangent x. And in the denominator, I have cosine squared x. So therefore, the left-hand side does equal the right-hand side, and I'll bring that down. Secant x minus tangent x over cosine squared x. And our proof is done. Include with your notes of this video guided practice problems 1 through 9 odd on pages 926 and 927 of your textbook.